Hi, in this video we're going to talk about multinomial and hypergeometric distributions. I mentioned in a previous video that I will give you the formulas for the expected values and variances of the random variables that follow these distributions, but I really expect you to be asked a problem. If you see this type of distribution, I expect it to be in the context of asking you for a probability of some event associated to the random variable that follows one of these distributions. And so with that in mind, I strongly encourage you to go back and look at the replacements examples video in the general probability module. It's one of the last videos in the general probability module. And in that replacements examples video, we actually did probabilities with multinomial and hypergeometric distributions. I just didn't tell you that that's what we were doing at that time. But I'm going to refer back to that video several times within this particular video. Okay, so let's go ahead and get started though and kind of discuss these distributions in more detail. So let's start with an example. Let's say that I have an urn that contains 25 red balls and 15 black balls, and a ball is going to be randomly selected from the urn. Its color is going to be recorded, and then it's returned back to the urn. This process is going to be repeated 12 times, and I want to define cap n sub cap r to be the random variable representing the number of red balls recorded. And the question here is, what we're ultimately going to get to is to determine the expected value and the variance of this random variable. Okay, now before I do that though, let's just kind of focus on the process here and the random variable cap n sub cap r. So what we have here, I hope it's clear to you that we have a sequence of trials. We have 12 independent trials. They're independent trials because the outcome from one trial does not depend on the outcome from the previous trial, because the ball is being returned to the urn. And so we have 12 independent trials, and in this case, each trial ends in one of two outcomes, either a success or a failure. So this random variable then follows a binomial distribution. I've exactly described a binomial distribution. And so it's, from previous videos, we'll be able to determine the expected value and the variance of the random variable. Just use those formulas from the previous video, which you'll see in just a second. What I'll need is, the notation I'll need is the p-value, or the probability of what I'm going to call a success. And since the random variable is counting the number of red balls, then I'll count as a success an outcome of a red ball, and the probability that you have a red ball selected is 25 out of 40, or 0.625. That's going to imply that the q-value, of course, is 1 minus the p-value. You think of it that way, or the q-value is the complementary probability, the probability that, in this case, a black ball is selected from the urn. The random variable, like I said, then it follows a binomial distribution with parameters m equals 12. There are 12 independent trials, and p being 0.625. We know from previous video that the expected value is a product of those parameters. So in this case, I mean, kind of think there's an you should intuitively see that the expected value is 12 times p is the probability of a success on an individual trial, and you have 12 trials, so 12 times p would be the expected number of outcomes, expected number of successes then of those 12 trials. Plugging in the values for m and p, we get a 7.5 for the expected value. The variance from previous video is the m times p times q. I'm going to start writing this as an m times p times 1 minus p, because the q is really not a new parameter. The q is 1 minus p. Once I know the p-value, I know the q-value. So I'm going to start writing this variance as an m times p times 1 minus p. Plug in the values here, and we get a 2.8125 for the variance. I want to make one more comment before I move on. If you look at other study sources, textbooks and such, they may use, where I'm using the m value, they may use an n value. Now, I'm using the m value because, to me, when I think of a lowercase n, especially when I'm using the capital letter N as a random variable, when I see the lowercase n, I'm thinking that n as being a value of the random variable. And so I'm using the capital N here as denoting my random variable. So I don't want to use an N as the number of trials, which is independent, completely different than the than the a value of the random variable. So that's why I'm using an M. And actually, when you start studying for later exams, and in particular when you start studying the short-term actuarial mathematics, they actually use this M as the parameter for the binomial distribution. So although you'll see maybe an N value in maybe statistics courses and textbooks, where I have the M, you might see an N. Later on, you'll see this notation that I'm using, the M value for the number of trials. Okay, so now let's go back to the, let's kind of clean up the slide a little bit. So I haven't changed anything. I'm just kind of took off the work that we've done and described the example. And now what I want to do is let's tweak this example a little bit. And now there are different ways to tweak it. One way to tweak this example is to add some more balls to the urn of a different color. And so let's add 10 green balls to the urn. So now I have red balls, black balls, and green balls. I'm going to do the same thing. I'm going to randomly select a ball from the urn. I'm going to record its color, and then I'm going to return the ball back to the urn, and I'm going to do this 12 times. Once again, cap N sub cap R is going to denote the random variable representing the number of red balls recorded. So once again, I have 12 independent trials, but this time each trial ends in one of more than two, in this case, 3 outcomes. And when that's the case, what we're talking about is a multinomial distribution. So this is just an extension of the binomial distribution where you do still have independent trials, but now each trial doesn't end in one of 2 situations, success or failure, but it ends in one of more than 2. And again, in this case, there would be 3 trials. I mentioned again that you're probably going to be asked to calculate a probability associated with something like this. Now, I can't give you we can't just talk about what the probability that cap N sub cap R is equal to 5, for instance, because, well, that would represent what's the probability that you have 5 red balls, but you're not given then the distribution, you're not given how many black balls and green balls did you choose. And so the probabilities that you're asked to calculate would be something like this. What's the probability that cap N sub cap R, the number of red balls is 5? And I'm sure you can see my notation. So this probability would be, what's the probability that 5 red balls, 4 black balls, and 3 green balls were recorded? So this was done in that previous video that I mentioned before, the replacements example video. And so I encourage you to go back and look at it. I'll quickly kind of go through the calculation here, but if you don't get it, then go back and look at that replacements examples video. And so the idea, though, is that you have 12 slots here, and you're going to, in those 12 slots, you're going to place 5 reds, 4 blacks, and 3 greens are going to go in those slots. Those are the colors that are recorded. And then if you look at probabilities of each selection being a red ball, it's 0.5, 25 out of the 50. Now I have 50 red balls, so 50 total balls. 25 out of the 50 are red. 15 out of the 50 are black, and 10 out of the 50 are green. So it gives these probabilities 0.5, 0.3, 0.2 for the probabilities of selecting in an individual trial a red ball, a black ball, or a green ball. And so since you have in those 12 slots, you have 5 reds. Well, each red comes with a probability of 0.5. So you're going to have 5 factors of 0.5. You're going to have 4 factors of 0.3, and then 3 factors of 0.2. And so your probability becomes this, where what I have highlighted in blue now are the number of distinguishable permutations of rearranging those R's, the B's, and the G's in the 12 slots. So that's the actual way that you would calculate a probability with respect to a multinomial distribution. And again, I encourage you to go back to that previous video if I went through that too quickly. Numerically, go through the calculation, and we got a 0.056 number for that. Okay, so now let's go back to the question, though, of, well, what would the expected value and the variance be for this random variable then? And so let's kind of, all we did is we extended the binomial distribution by assuming that each trial doesn't end in one of two outcomes, but one of more than two, or an outcome of a certain type, where there's more than two types of outcomes possible. So generally, a multinomial distribution and the expected value and the variance will be given this way. So we have a multinomial distribution where there are m independent trials, with each trial ending in outcome type I with probability p sub I. That's exactly what we did a little while ago. We had red balls with probability p sub r and so forth. And then if cap n sub I denotes the random variable representing the number of the m outcomes, how many of the outcomes were of type I, then you could see this is exactly the same. This is completely analogous. The expectation and variance formulas are completely analogous to the binomial distribution. So going back to our example here, this is a multinomial distribution. We're looking for the expected value and the variance. The random variable that we're talking about is the one that counts the number of red balls recorded. And so I need the p sub r value of 0.5. So we have this multinomial distribution now with parameters m equal 12, still 12 trials. Probability of a red ball being selected is 0.5. So the expected number of red balls selected will be 12 times 0.5, or 6. And the variance of the number of red balls selected, the random variable representing the number of red balls selected, would be the m times p times 1 minus p calculation, with a p-value being 0.5. And go through that calculation, you'll get a 3. If I change, so watch what I do when I go to the next slide. I'm going to change the random variable from a cap n sub cap r to a cap n sub cap b. So now I'm counting the number of black balls that are recorded. But very similar now, since my random variable is counting the number of black balls being recorded, then my p-value is going to be the probability of selecting a black ball on a individual trial, which was 0.3. So now I've got a multinomial distribution with parameters m equal 12 and p being, I'm using the p-value of 0.3. Again, the expected value is the product of the parameters, so that's 12 times 0.3 or 3.6, and then the variance would be a 12 times 0.3 times, what would that be, 0.7, and I got a 2.52 when I did that. Okay, so that's the multinomial distribution. Now let's go back to the original example that ended up being a binomial distribution, and let's think about how we could tweak it another way. So we tweaked it to get a multinomial distribution by adding another set of green balls to the urn, and recognizing that now our outcomes, each outcome could end in one of three types instead of one of two types. So that was the multinomial. Now we're going back here. How else could we tweak it? Well, one way we could tweak it is, in this example, each ball is returned to the urn before we select another one. Well, another way we could tweak it is that it's not returned to the urn. And so, again, we talked about an example like this in the previous video, in the replacements examples video. And we showed that mathematically, when you have this situation, you're taking a ball from the urn, recording its color, and then not returning it to the urn, and then selecting another ball. So mathematically, this is going to be exactly the same as just taking 12 balls out of the urn at one time. Just 12 balls are randomly and simultaneously selected from the urn and recording their colors. So mathematically, those are exactly the same thing. And so I'm going to switch back and forth actually between those two descriptions of the tweak that we just made. So we'll go back to this description, that a ball is randomly selected from the urn, its color is recorded, but it is not returned to the urn, and the process is repeated 12 times. There's still 12 trials, and each trial here is going to end in a success or a failure, depending on how I name the random variable. In fact, in this case, the random variable represents the number of red balls selected, so I'm defining a success to be when I pick a red ball out of the urn. But now, because I'm not returning the balls to the urn, the trial outcomes are no longer independent of each other. once I have a red ball, if I choose a red ball out of the urn, the probability that the next ball is red is no longer 25 out of 50 anymore. So the trial outcomes are no longer independent of one another. So we would say there are 12 dependent trials, with each trial ending in either a success or a failure. This is describing what's called a hypergeometric distribution. And so a hypergeometric distribution, again, if you see this, you're probably going to be asked to calculate some probability associated with this, with the random variable that follows this distribution. For instance, I could look at what a p sub 5 value would be, or the probability that the random variable is equal to 5. This is just saying, well, what's the probability that that 5 red balls were selected? And I encourage you again to go back and look at the video from the replacements examples. And I described the process that I would use to do this. This is just some event that we're taking the probability of, and it ends up being this fraction. In the numerator is the number of ways for the event to occur, and in the denominator is the number of outcomes in the whole sample. And so the denominator, for instance, is, well, out of the 40, there's 40 balls total here, and out of those 40 balls, we're selecting 12. So that's the denominator. Now, what's the event? Well, the event that 5 of them were red and 7 of them then were black. If 5 were red, then automatically 7 are black. And so what are the number of ways of doing that? Well, out of the 25 red balls, I need to select 5. So that's I'm using this notation for the number of combinations. So the 25 over 5 there, I would read as 25 choose 5. It's the number of combinations of 25 elements chosen 5 at a time. So 25 choose 5 because there were 25 red balls that I'm choosing 5. And then I'm going to take, I want to choose 7 black balls, and out of the 15 black balls, I choose 7. And so that's the ratio. Again, if I'm going through this and you're not picking up on it, then please go back and look at that other video. Numerically, I got a value. I got a misprint there. It should be a 0.061 ... instead of the ... 0.061. Okay, so that's a hypergeometric distribution. Let's kind of go back to the question that I'm in this. Now I'm going to seek the values of the expected value and the variance of this random variable. So when I get to the general description, the next slide is going to be the general description of a hypergeometric distribution. But before I do that, let's kind of let's kind of go over the situation here. I'm choosing 12. I'm selecting 12 balls. I'm thinking of selecting 12 balls out of this urn, and the urn has a total of 40 balls. I'm counting the number of red balls that are in the urn, and the 40 balls can be split up as 25 red, and then 40 minus 25, of course, is 15 black. Okay, so let's keep that in mind when I go to this general description, because the general description can get kind of confusing. But here we have a hypergeometric distribution where there are m objects being selected from n total objects, where the n total objects consist of capital K objects of one particular type, and then cap n minus cap A objects of another. And if we define cap n sub 1 to be the random variable representing the number of the m objects that were selected that are of that one particular type, let's say red, then if we would define the p-value to be k over n, then the expected value of the random variable is going to be, again, an m times p, and the variance is going to be very close to an m times p times 1 minus p, but you have this extra factor on the n, cap n minus m divided by cap n minus 1, that factor on the n. I'm just giving you the punchline. I'm not trying to prove anything to you, but that's the punchline. So if we go back to our example here, we got a ball. Again, a ball is randomly selected from the urn, color recorded, and so forth, but it's not returned. And we said, well, that's the same thing. It's just 12 balls are randomly and simultaneously selected from the urn. So my m is 12. I'm selecting 12 balls, and the n is 40 because cap n is 40. Cap n is the total number of objects I'm selecting 12 from the 40, and then cap K is going to represent the type in question, which the random variable is defined as the number of red balls, so cap K would be the number of red balls. So you're going to see this as the random variable cap N sub cap R is hypergeometric with parameters M, cap N, and cap K. In that case, how I teach this is I say, well, just let's talk about the probability of selecting a red ball. That would be K out of N, K divided by N, or 25 divided by 40. And then the expected value of the hypergeometric, again, it's very similar to the binomial. The expected value is just going to be an M times P again. So M times P would be the 12 times 25 over 40. I got 7.5 there. The variance is going to be almost the M times P times 1 minus P, but I have this extra factor on the N. Cap N, or 40, minus M, which was 12. And then divide that by 39 in this case. And what I get when I plug in these values is a 2.019 number. Okay, so that's the hypergeometric distribution. So let me kind of summarize here. In the example 1, when we just had a success-failure situation, and we were selecting 12 balls, they were independent trials. So if you have independent trials, each trial ends in success or failure, you're talking about a binomial distribution. Oh, I'm sorry, I went too fast. Talk about a binomial distribution, the way you calculate the probability that the random variable is equal to K, that's the P sub K. These are formulas from before. That formula for P sub K we saw in a previous video, and then we have these formulas for expected values and variances. Now, we wanted to tweak this, and one way that we could tweak it is to add more balls to the urn, add more types of outcomes on the trials, and then we end up with a multinomial distribution. But again, the multinomial distribution, I've given you an example of how to calculate a probability with that multinomial distribution. I don't want to get into what the formula would be in the general case. I think once you see how to do it in this specific case, you can extrapolate to other cases. And the formulas for expected value and variance are very similar. They're the same with using a certain p-value there. And then another way we could have tweaked the distribution, or the example 1, was to make the trials dependent. So when you have dependent trials, and each trial ends in either a success or failure, you're talking about a hypergeometric distribution. And here's the formula for calculating the probability that the random variable is equal to a K. Again, let's move on to the lower two formulas. These are the formulas for the expected value and the variance, but the P sub K, it looks complicated, but it's really not that complicated once you have a specific example, like a P sub 5 was how we calculated this P sub 5. Okay, so finally, there's one other way that we could have tweaked to the example, one more natural way to tweak that first example, and that's to do a combination of adding balls to the urn and the combination adding more balls to the urn and not returning a selected ball to the urn before we select another one. And so we would have dependent trials here because we're not returning the ball to the urn, and dependent trials, but then each trial ends in more than one of two types. So dependent trials means I'm not binomial or multinomial, but like a hypergeometric, and this is actually called a multivariate hypergeometric distribution. And in this case, if this was the setup, you're not going to be asked the expected value of variance. You're going to be asked a probability associated to this, but I think that's a fair question. And the probability, for instance, I'll give you the example, the probability that in this case you selected 5 reds, 4 blues, and 3 greens. I've given you this expression here, and this was exactly a problem that we did in that replacements examples video. This was a problem in the replacements examples video. So if you don't see the way to extrapolate from what we did in the hypergeometric distribution to the multivariate hypergeometric distribution, please go back and look at that video. All right, well, that was a long video. Apologize for that, but they do belong. I think you can see all of that material does belong in one video. All right, well, I'll see you in the next video.